Welcome back to the deep dive. Our journey today, it actually started not in some high-tech lab, but really from a moment of, well, philosophical curiosity. A listener told us they were at a David Bowie tribute show, heard that line, "Time can change me, but I can't change time." And it just hit them. That feeling, right? You hear a certain sound, maybe a guitar riff or just someone's voice, and bang, you're transported. The sound feels timeless, fixed, instantly recognizable. And it sparked this big question. What if our brains don't just store audio recordings? What if we recognize sound based on its fundamental shape, its geometry? That's what we're diving into. Sound shapes.
That's exactly right. Our mission, really, for this deep dive is exploring this idea of a universal blueprint, a mathematical one. Think of it as a geometry of sound, something that could let us classify any sound objectively. A symphony, sure, but also a bird call or just the way someone speaks. And it's needed because, frankly, our current tools, they fall short. Music notation is great for pitch, rhythm.
But not timbre or texture.
Exactly. It ignores so much. And then we have these really vague, subjective genre labels. Rock and classical. What does that even mean acoustically? We need something objective, something rooted in the waveform itself.
Okay, so moving from subjective listening to something more rigorous, mathematical, that brings us to this core idea. Auditory topology. Before we jump into all the shapes, can you maybe unpack that term for us? What is topology doing here that, say, traditional sound analysis can't?
Sure. Think of it like this. Traditional physics might tell you what something is, its pitch, its volume. Topology tells you what shape it is. It's a study of properties that stay the same even when you stretch or bend the shape, as long as you don't tear it. The classic example is a coffee cup and a donut. Topologically, they're the same shape because they both have one hole.
Okay. So how does that apply to sound? You can't exactly stretch a sound wave like dough.
Well, not physically, but mathematically you can. Auditory topology gives us a framework, a kind of map and coordinate system for sound. It provides a rigorous way to filter out random noise and isolate the meaningful pattern of the sound shape. And crucially, it lets us define the distance or similarity between two totally different sounds.
Like how similar a spoken word is to a trumpet note.
Exactly. Based purely on their waveform geometry, not just, are they high or low pitched, it quantifies that similarity.
I see. So you're giving us coordinates for the soundscape. Okay, let's get into the architecture then. You mentioned 3 fundamental shape families that can define pretty much any sound, music, or speech. What are they?
Yeah, we pull these directly from advanced signal processing. The first is the amplitude envelope. So it's basically the contour of loudness over time, how the sound starts, how it peaks, how it fades away.
It's like a snare drum hit versus a cello note.
Perfect example. The snare has that super sharp instant peak, then it dies quickly. The cello. Much slower attack, a gradual swell, maybe a long sustain. Totally different loudness shapes.
Okay, that makes sense. What's the second family?
The second is spectromorphology. This one's about how the sound's energy is spread out across different frequencies. Imagine plotting frequency versus energy. A pure flute tone. It'll look like a narrow spike. Most energy is focused right there.
Right.
But a cymbal crash, that's going to look like a wide, fuzzy cloud. Energy scattered all over the place. That difference in spectral shape is fundamental.
And the third one is melodic contour. This feels really important because it seems to bridge music and speech directly.
It absolutely does. Melodic contour isn't about specific notes like C sharp or F flat. It's the overall pitch shape. Does the pitch generally rise? Does it fall? Does it kind of undulate like a wave? Or stay flat?
Like when you ask a question in English, your voice tends to go up at the end.
Exactly, that rising intonation. That's a melodic contour. And you can compare that shape directly to, say, a rising musical phrase in a song, regardless of the instrument or the exact notes. It's the pattern of movement.
Okay, shapes identified. But to make this useful, especially for computers, we need to measure them precisely. You mentioned some metrics. Fractal dimension sounded pretty intense. What does that tell us?
Fractal dimension, yeah, it sounds complex, but the idea is simple. It quantifies complexity or jaggedness. A really smooth, predictable waveform, like a pure sine wave, has a very low fractal dimension. It's simple,
Okay.
but something chaotic, like glass shattering or static on the radio. That waveform is incredibly complex, very jagged. It has a high fractal dimension.
So it's a single number that tells you how messy or organized the sound wave is.
Pretty much. It helps distinguish highly structured sound, like, a Bach fugue, from just random noise. big difference in their fractal dimension.
That makes it much clearer. Okay, what about the others? Spectral centroid and spread.
Right. Spectral centroid is like the center of gravity for the frequencies in the sound.
Yeah.
If the centroid is high, we tend to perceive the sound as bright or sharp, maybe like a piccolo. If it's low, the sound feels darker, rounder, like a tuba.
And the spread.
Spread tells you how concentrated or spread out those frequencies are around that center point, that centroid. Low spread means the energy is focused, like a laser beam. High spread means it's diffuse, spread out.
Like the difference between that flute tone and the cymbal crash again?
Exactly. Flute, low spread, cymbal, high spread.
Got it. And the last one, autocorrelation. Sounds like it measures repetition.
It does, precisely. Autocorrelation checks how much a pattern repeats itself over time. On a simple level, it helps identify a steady rhythm or maybe a looped sample in electronic music.
Okay.
But more abstractly, it can find deeper patterns. It could mathematically link a simple repeating drum beat to the way motifs repeat and weave through a complex classical piece, like that Bach fugue again. It measures the internal coherence, the self-similarity over time.
So we have shapes. We have ways to measure them.
Yeah.
How does this build up into a full system? You talked about a library root of basic sound atoms. What are these fundamental bits?
Yeah, the atoms are the simplest irreducible sound shapes. We're talking things like an impulse, just a quick click or pop, a swell, the gradual rise in loudness, a drone, a steady, sustained sound, a noise burst, and a glissando, that smooth slide in pitch. These are like the basic Lego blocks.
And complex sounds are built by combining these. How does that connect back to that initial Bowie quality idea, that instantly recognizable sound?
Right. That distinct quality isn't just one thing. It's a specific recipe, composition. It might be defined mathematically as, say, an impulse attack, immediately followed by a rapid swell, leading into a drone, but one that has a very specific filter applied to its spectral morphology, giving it that unique timbre.
So it's the combination and the precise mathematical modifications of these simple atoms that creates the complex recognizable signature.
Exactly. We move from fuzzy words like bright or gritty to a computable structure, a mathematical formula that sounds signature, regardless of volume or context.
This is fascinating. Now, let's pivot slightly. Applying this geometry idea not just to music or general sounds, but specifically to human speech. This leads to the Phonetic Shape System, or PSS. The goal here, as I understand it, is a universal phonetic script, something maybe even beyond the standard International Phonetic Alphabet, the IPA. You called it a living Rosetta Stone.
That's the ambition.
Which is a powerful idea. But how does a dynamic, maybe even animated symbol actually convey more than a static IPA symbol, which is already internationally recognized? What's the real game?
The game is moving beyond arbitrary symbols. IPA symbols are essentially just letters we've assigned to sounds. PSS is built on what we call isomorphic representation.
Meaning
the visual shape of the PSS symbol must logically connect to the sound itself, its acoustic shape, how it sounds, and crucially, the articulatory shape, how your mouth actually produces it.
So the symbol looks like how you make the sound.
In a way, yes. It's a diagram, not just the letter. If you can see the shape, understand the movement it represents, and hear the sound simultaneously, you're capturing the whole linguistic mechanism. That's why PSS glyphs have 3 layers.
Okay, walk us through them. Layer 1 is the physical part, the vocal tract map.
Correct. Layer 1 is the articulatory base glyph. Think of it like a simplified diagram, a side view map of your vocal tract. It shows the manner of articulation, how the air is manipulated. So a plosive sound, like P or B, the symbol would visually suggest a blockage, a pressure buildup, then a burst or release.
Right.
A fricative, like S or F, the symbol would show a narrowing, suggesting that turbulent airflow. And modifications to this base shape show the places it happening at the lips, behind the teeth, further back.
Okay, so that's the how and where. What's layer 2?
Layer 2 overlays the acoustic details. We call it the sound aura. This adds information like voicing, are the vocal cords vibrating or not. Voicing might be shown by making the line of the symbol thicker or maybe wavy. An unvoiced sound, like P or S, might have a thinner or hollow line.
And vowels. They seem tricky.
Vowels are key for layer 2. They're mainly defined by their first 2 resonant frequencies, called formants, F1 and F2. Now, don't worry too much about the term formant. Just think of them as the main frequency peaks that your vocal tract shape emphasizes. Our brain uses the relationship between F1 and F2 to tell E from ah, from oo.
Okay, so F1 and F2 are critical acoustic clues. How does PSS visually represent them?
It maps them directly onto the glyph's shape and position based on how they relate to physical articulation. F1 generally correlates with how open your jaw is, or tongue height.
Yeah.
So F1 maps to the symbol's vertical position, or maybe its height. Higher F1 usually means a lower jaw, more open. F2 relates to how far forward or back your tongue is.
Right.
So F2 maps to the symbol's horizontal position or width. By placing and shaping the vowel symbol according to F1 and F2, the visual glyph becomes a direct map of the vowel's acoustic shape and gives you clues about the tongue and jaw position needed.
Wow, okay, so it's encoding the sound and the production method visually. What about layer 3, dynamics? You said the symbols aren't static.
Exactly. Speech isn't a series of isolated sounds, it's fluid. Layer 3 is dynamics, showing movement and transitions. This captures things like co-articulation, how making one sound influences the sounds right next to it.
Like how the A in cat is different from the A in cat.
Precisely. Your mouth is already getting ready for the next consonant. PSS aims to show this. A diphthong, like the oi in boy, isn't two separate vowel symbols. It's shown as one symbol smoothly morphing, animating from the O shape to the A shape.
So you see the movement.
You see the movement. Take a simple syllable like ba. The PSS symbol wouldn't be a static B, then a static A. It would animate as a single, continuous motion, starting with the lip closure shape for B, then smoothly opening into the vowel shape for A. That animation is the kinetic sequence. It shows the physical action of speaking, something totally missing from static symbols.
Okay, let's talk impact. We have the system. Sound shapes as elements, math functions as the rules connecting them, and it models the physics of the vocal tract. How does this actually change things? You mentioned AI translation.
Right. Traditional AI translation is mostly statistical. It learns this word in language A often translates to that word in language B. It's like a giant, complex dictionary lookup.
Yeah, and sometimes the nuance gets lost.
Totally. PSS enables a different approach. Think of it like a linguistic compiler. The process would be analyze the source sound shape sequence, figure out the underlying articulatory gestures that produced it.
Your physical movements.
Yes. Then translate those physical gestures into the corresponding gestures required by the target language, and then generate the target sound shape sequence from those target gestures.
So it's translating the mechanics of speech, not just the words?
Exactly. Because it's working at the level of physical production physics, it can preserve much more nuanced emotional tone, prosody, the rhythm and melody of speech, things that statistical models often butcher. The goal is translation that sounds physically and emotionally authentic.
That sounds like a huge leap, but maybe the most powerful application you mentioned ties back to preservation, especially for endangered languages, capturing the kinetic knowledge.
Yes, for me, this is incredibly important. When the last speakers of a language pass away, we obviously lose the words, the grammar, but we also lose something intangible, the knowledge of how to physically make the unique sounds of that language.
The specific way they move their tongue or shape their lips.
Precisely. An audio recording tells you what it sounded like. It doesn't teach you how to do it yourself. That kinetic knowledge vanishes. PSS, by encoding those articulatory gestures directly into the animated symbols, offers a way to capture that how-to. It allows for creating living lexicons.
Animated pronunciation guides.
Essentially, yes. Guides based on the actual measured articulations of native speakers. Future generations wouldn't just hear recordings. They could see visually how to move their own vocal tracts to reconstruct the sounds, the voice of their ancestors.
It feels like this moves beyond just linguistics into cultural heritage. Does it align with any broader initiatives?
Absolutely. This kind of work aligns perfectly with global efforts like UNESCO's 2003 Convention for Safeguarding Intangible Cultural Heritage. Language, especially the spoken aspect, is a core part of that, and is particularly relevant now during the International Decade of Indigenous Languages, which runs until 2032. PSS offers a potentially powerful modern toolkit to help document, preserve, and even revitalize languages by capturing that often lost phonetic and articulatory detail. It's about providing rigorous scientific tools for a critical cultural goal.
It's really something, tracing this whole deep dive from that listener's feeling at the Bowie Show, that sense of timelessness and sound, all the way to a potential system, a computable model of vocal production, a system that could genuinely shift how we teach language, how machines translate, and how we preserve this fundamental part of human culture.
And it leaves us with a rather provocative thought, doesn't it? If this science lets us map the precise physical gestures for all the sounds in modern languages, could we work backwards? Could we use this geometric understanding to potentially reconstruct the physical articulations, maybe even approximate the actual voices of ancient proto-languages, Imagine hearing not just the reconstructed words, but the potential physical sound of how our distant ancestors might have spoken.
From a sound shape at a concert to the voice of ancestors. Definitely something to think about.